Now if I want to design the same thing using op-amp RC integrator, so let's copy this. So this is GMC integrator. So this is your VREF. Do I need to have a resistor here? I already have a feedback resistor. I can use it as an integrator. So all I need to have just one feedback capacitor. Okay, this is nothing but your CI. What will be the value of CI? So R is 1 over RC, GM by C is 1 over RC here. So R is 100K, GM was 10 micro. So if you go with the formula GM by C equal to 1 over RC, then your CI will be same. Okay, but will it be same?
It is around high negative.
Sorry? What?
Means that the input of this op-amp for the capacitance, that it will be higher than due to Miller effect.
But how does it matter? That's how you form the integrator. Your capacitor is very high. If you have infinite gain, that's why you get the integrator. So you replace this op-amp feedback resistor with R and C, okay, and C is very high. So you will get a first order low pass filter with a very low cutoff frequency, and that is nothing but integrator. What is the beta factor here? If you do the loop gain analysis, is it half? So if you break the loop, what is this point? If you do a small signal analysis, what is this? So VREF is 0 for AC. With the virtual ground, what is this? 0. So no current is flowing in the bottom resistor. So beta is killed. There is no beta here. So beta is 1. No beta means not 0 actually. The feedback factor is 1 here because this resistor no small signal current due to virtual ground. So beta equal to 1. Okay. So which means your KU0 is nothing but VDD by VM here. So there is a difference if you do a GMC and op-amp RC, correct? So now what? So now beta is 1. So what should be the CI? With the half you are getting this 2.97. So beta equal to 1, it should be twice of that, which is 5 point how much? 94. correct? Okay. Now go back. So I have a op amp RC, I have put 2x cap here. So when I do the loop gain analysis, the frequency response should match. So I have already run, I will just do the. So this is your op amp RC, they are overlapping. So only difference you see at low frequency, which is due to this resistor, because this is ideal integrator and this is non-ideal. That's why you are seeing that. But you are more interested in this peaking and UGB, so it's crossing at the same value, UGB, and your gain margin is same. Correct. So you have to be a bit careful when you do GMC or op amp RC, because beta will not be in picture in case of op amp RC, but in this case you have to include that. Okay, so this is the complete switching circuit with your op amp RC integrator. So this is your power stage where I have ideal switches with 50 milliohm RDS on here, and this diode I have connected because during non overlap time, if I do not have this, it will not conduct and this voltage may go some megavolt, kilovolt, and your circuit will not converge. So whenever you are using ideal switch, make sure you connect in parallel, and this is nothing but the body diode of your MOSFET, so that you allow the this diode to conduct. I think the bottom one is more important because during dead time that will conduct. So just make sure at least you have in the bottom switch. Rest of the values are same. 50 milliohm this and 50 milliohm is DCR, 5.94, and this is nothing but sawtooth with 1 volt magnitude, and this is simply comparator, and this is your gate driver with non overlap time. Okay. So it should be stable. Okay. It may have some ringing around resonance, weak ringing, because you still have that peaking. So if you do not want to see the ringing, you have to kill the gain even more, like maybe minus 40 dB or so. With minus 20 dB, you will still see some ringing. So this is settled at 1.2 volt. Okay. You can see some ringing here. It goes away. If I keep reducing the gain or increasing the value of this capacitor, then that ringing should reduce. Now let us say if I have I do not include that 10 factor, means 0 dB if I have gain margin, then what should be the value of this? One over 10 times, correct? So it should be unstable with this, so we can check. Okay. And if you further reduce this, make it gain more than 1. So let us say I make it 100 picofarad. Then the oscillation magnitude, amplitude will start increasing. So it will become an oscillator actually. Okay. So it will never settle actually. You can see it's plus minus 50, 20 millivolt or so. Okay. So to summarize, integral or type 1 Okay, due to because you don't have any option here, you have to push your LC pole outside your UGB and you want to have enough gain margin, so you have to kill the bandwidth, otherwise there is no option. Poor transient response. So, if I give a, let us say, a load or line transient, so your loop will not respond very fast. So, it will take some time to change your duty cycle or recover the current, which means your capacitor has to supply that current for a larger duration and your output voltage will dip more here. So, your undershoot overshoot will be large in this case and your settling time will also increase because your loop is very slow. So, control voltage will not change very fast, which means your duty cycle is not changing fast enough, inductor current will not change faster, so it will not recover. And if you want to see, we can see here in this case the load transient also. So, let me make it half amp and so I will make it 10 nano roughly, which is more than what we calculated. So, that ringing is not that high. Okay, so, you can see I am applying the load here, releasing here. So, it dips and then rings and settle, and this ringing should be at resonance frequency, you can check it. So, as I keep on increasing this capacitor value, this ringing eventually may go away at very large value, let us say 100 nanofarad also, which will make it even worse in terms of bandwidth or transient response. So, only suitable for low bandwidth system. Okay. So, what could be the low bandwidth system, which is only fixed load your example could be let us say battery charger. Okay. So, you are simply charging the battery, but you are not supplying any load, and charging is usually battery is charged with a fixed current. So, your load is not changing, your current will remain constant, or your LED light, let us say. So, you on and off, that is it, there is no change in the load. So, the moment you turn on, it will settle to certain current, turn off, it will current will go to 0, that is it. Okay. So, it is simpler to implement, requires only one cap, but since the cap value is too large, if it is order of nanofarads, you cannot integrate on chip. So, most of the time with this type of compensation, you require off chip capacitor. In case of GMC, you can kill the GM, let us say you make it 10 nano or so. Okay. So, you can get a cap value of order of picofarads. So, 10 micro I have put here, if I make it 10 nano, it will be 1000 times less. So, whatever value we calculated 2.97 nanofarad, it will become 2.97 picofarad. or if you make 100 nano, then 29.7 picofarad, which is not bad actually. I mean, up to anything less than 100 picofarad is okay, and if it's tens of picofarad, that is more preferred because these caps take a lot of area. So, you can with the GMC you can achieve, and if you want to go with the op amp RC, then this R value should be very large in that case, okay, and which means this R will take more area. So, it's better to reduce the GM in that case, but there is a problem if you go with a very low GM. No, noise is the other thing. What about offset? We talked about when we are, you need a large GM because any mismatch will introduce more input referred offset, okay, because your current, if you have a differential stage, your current is nothing but GM times V in. If GM is very low, any mismatch in the current will get reflected into V in, and that V in will be large in that case because GM is very low. So, even a small current mismatch can introduce a large offset. So, that is why we prefer large GM, but you will not have that problem with the op amp RC if you use a very large R, because you are not changing the characteristic of the op amp, you are simply changing the R and C values, that is it.
Why that anyways that will be virtually grounded, so why we need to keep a very large resistance?
Which one?
Feedback resistance, and that is that feedback resistance should be very high.
You mean this one?
Yes.
Yeah, you can keep it, that is what I am saying. You make it 10 mega ohm or so and reduce the C value. Ultimately, you are looking at a 1 over RC product, that is your Ki. So, either you increase the R or increase the C, choose the lower, okay. You can choose mega ohm, that is not a problem, but if you are integrating on chip, then this resistor will take lot of area, tens of mega ohm. With off chip resistor is fine, but the problem then when you go off chip, it has more tendency to pick up the noise from external environment, and if this resistor value is very high, then this node becomes in that case more sensitive, okay. So, when you go external, you usually choose mega ohm also, okay, but on chip you cannot put, like, you can do 1 mega ohm we do actually, but tens of mega ohm is very unlikely, this will take a lot of area, okay. And higher the value is, this node is, you making that node basically weaker, so it can pick up noise very easily. So, which means this input impedance will be very high,
So noise will be
so it can pick up any noise very easily. So, you have to be a bit careful when you make any node very high impedance, you have to be a bit careful in terms of noise. You have to, even the layout and all those, we have to do it very carefully, because this is very sensitive noise, and any noise will get injected directly into your PWM, and it will get reflected on your output, if you, especially if it is a low frequency noise, okay, everything will pass through your loop, and this LC will not be able to filter. If it is, let us say, order of megahertz, then LC bandwidth is very low, it will filter, but if it is order of kilohertz, then you can see in the output that noise. So, your loop will pick up and your output will be very noisy, okay.